So next up, adding and subtracting radicals. When we do this, we want to think the same way we think when we combine like terms in algebra. So I've got a couple of examples here just to kind of ease us into this. In an algebraic expression or an equation, like this, we can combine the 3x and then minus 6x, and we can turn that expression into a simplified version where it's negative 3x plus 7 equals 12, and then we could go ahead and try to solve that for x. It won't be a pretty answer there, but the gist of it here is I want to point out that the 3x and the minus 6x combines to a minus 3x. That's combining like terms. Same thing down here, when we've got a's and b's in an equation like this, we can combine the a's and we can combine the b's. And in fact, I guess we've also got standalone coefficients with no variable, like the 5 and the minus 9. So maybe that's where we'll start with this one. So the 5 minus 9, that would give us minus 4. The a's we can combine. We get a minus 7a minus 2a, so that would be minus 9a. And then we've got a positive 6b, subtract 3b, so that would be plus 3b equals 4. And we could try to solve this for a or b. It wouldn't end up being anything very pretty here. The point is, in this, I just want to remind you that you can combine like terms in an equation, and that's how we're going to deal with radicals here next. So let's look at some examples with radicals. The key with these is that you can only combine like terms when your radical is the same. So we could think of this first example here as something like 2x plus 12x. Right? They've got a similar radical. The radical in each is root 2. So that's like saying they've each got an x almost. So this would simply turn into 14 root 2, because we're saying it's 2x and 12x, that's 14x, or in this case 14 root 2. Now, in this next example over here, I've got cube root of 7 and cube root of 7, and 6 minus 8. So they are both cube roots, and they are both cube roots of 7. That's important. They need to be the exact same index and the exact same radicand in order for us to be able to combine them. So we can combine this into minus 2 cube root of 7. So we can do 6 subtract 8. Now, two examples here down below are examples where we cannot combine them. And I want to point out why. This first one, we've got 8 root 6 and we've got 8 root 5. That would almost be like saying 8x plus 8y, right? In an algebra sense, those are different radicands, so they may as well be different letters. You cannot add an x and a y. You cannot add a root 6 and a root 5. Same thing with this one. The reason we cannot combine these or subtract these radicals is because the index is different. This one is a cube root of 2 and this one is the square root of 2. The 2 is the same, the radicand is the same, but because the index is different, we cannot add them. So this cannot be done either. So neither of these bottom two can be done. You just kind of have to leave them as is, and that's an unsatisfying way to leave an answer sometimes in math, is to just say it cannot be done. But sometimes that's the case in these two examples. They cannot be added together or subtracted. Sometimes it looks like you cannot subtract or add two radicals, but when you switch them from entire radicals to mixed radicals, it may create a common radical. So this first example, you would look at this initially and say, well, I've got the cube root of 2 and the cube root of 54. Well, those are different radicands, so they can't be added. But if we took this this cube root of 54 and we noticed, just isolate that just for a moment. So just imagine we're just dealing with the cube root of 54. We can rewrite that as the cube root of 27 times the cube root of 2. We did this in the previous video. The reason we might want to do this is because we know the cube root of 27. We know that that's equal to 3. So I'm just going to rewrite everything back in here. So we're keeping track of everything. This is 5 cube root of 2 minus 2. And then so all I've done is rewritten this piece. That's the cube root of 54, and I've rewritten it as this. And then let's continue down onto the next line where we've evaluated that. So that would be the 5 times the cube root of 2 minus 2 times, and remember we said a second ago that cube root of 27 is 3. And then we've got the cube root of 2. Okay, 2 times 3, that's 6. So now again, we can rewrite this. I'll do one more step here. 5 cube root of 2 minus 6 cube root of 2. Oh, now we've got a common radicand under both these radicals. So we can take 5 subtract 6. That's minus 1 cube root of 2. You don't have to put the 1. I've left it out here, just like you don't have to say 1x. You can just say x. So this expression up here doesn't look like we can actually subtract them because they have different radicands, but if we notice that there's a perfect cube lurking in that 54, then we can simplify that down, and then it brings out a common radicand that otherwise we wouldn't have seen. Let's try that again in another example. We've got 3 terms this time around, and there's nothing we can do with the root 2, but with the root 8 and the root 32, there's a little bit of work that we can do with those, so let's do that. So we'll rewrite the 7 root 2. Now the 4 root 8, we know that root 8 can be broken down into root 4 and root 2. I'm going to kind of squeeze it in here now, I'm running out of room. And then the 32 can be broken down into root 16 root 2. We can evaluate these perfect squares, the root 4 and the root 16. When we do that, I'll just have to rewrite everything here. So when we do that, though, we're going to get 7 root 2 minus 4 times 2 root 2 plus 2 times 4 root 2. A lot in there. So again, rewrite it, next line, 7 root 2, we can't change that. Now we have minus 8 root 2, the 4 and the 2 come together to make an 8. And the 2 times 4 again makes another 8. So we have 7 root 2 minus 8 root 2 plus 8 root 2. Well, those just cancel one another out. So it ends up that we really just end up here with 7 root 2. So the whole moral of this one is that there are sometimes ways that you can turn your entire radicals into mixed radicals, and it reveals an otherwise hidden a common radicand or a common root that you can then add and subtract.